NanoHub U, online instruction.
Hey everyone, welcome to lecture 321. So now we're going to continue the theme of local density of states by looking at a different system which might be more interesting, which is an OmniGuide fiber. And so if you're not familiar with the OmniGuide fiber, this is what it looks like. So on the one end, on the kind of the cross-sectional view, you have periodic repetition of high and low dielectric layers. So it kind of looks like a distributed Bragg reflector. But the difference from the DBR is that it's actually rolled up into a tube. And so you can kind of see what the tube looks like on the right-hand side. So that's kind of looking from the long end down the length of the system. And so this is just setting up the coordinate axis. You can see the diameter is actually very small compared to the period. It's only 4a. A lot of the real OmniGuides that have been made are bigger. But what's interesting about this system is we may expect, because it has kind of this 1D structure and periodicity, to have a very strong enhancement of local density modes. And so if we assume that it's made out of very high contrast materials, then we can use a very small computational cell, even in 3D. And then we can put some sources at different locations at the end of the system. And then we can actually look at like what would be transmitted to the other side at this flux plane over here. And so what we actually had expected is to see a so-called 1D Van Hove singularity that corresponds to 1 over square root omega minus omega c type increase in the local density of states. And indeed, we can see that explicitly here. And so this is showing what kind of emission would happen in vacuum in all directions. In the case of the optical fiber, if you had like fiber coupling, you can see that you would capture some fraction of the light, but this is a log scale, so you're probably losing like 99% of the light. But in the case of the OmniGuide, you actually see more transmission than you would see just in the air. And that's purely enhancement of density of states effect. And so that actually tells us very explicitly that this is having a very strong effect. And this was also explained in more detail in the Physical Review B paper from 2004. And then if we look more explicitly at the density of states now, so remember from last time we had actually defined a local density of states that looks like this, where we have basically a Dirac delta function to capture all the bands that are at a certain frequency times the E field and the epsilon at that position. And then again, as I mentioned earlier, we predict this 1 over square root dependence, which is the Van Hove singularity. But we, of course, also have this dependence on the E field squared. And so, of course, the enhancement would be basically negligible if the field was also very small. But then we can actually see explicitly using two different calculation methods, one in the time domain using finite difference time domain, and then comparing that to frequency domain, that there's a very good match in the local density of states. So basically, in both cases, you see big jump in local density of states, and then there's like a fall off, and then a second jump, and then fall off. And so this frequency domain calculation was performed using methods similar to what was discussed in Unit 1, but actually explicitly integrating this sort of system using the Gilot-Raubenheimer method, which was actually originally proposed in Physical Review many years ago, probably in the 1960s. And of course, the modern paper that explains the details is from 2004. So in the next lecture, we'll kind of wrap up and see what we've learned in this unit and where we're going to go from there.